Hello everybody, welcome to section 7.2. Today we're going to talk about the law of cosines. Now, you'll see on the screen I have pulled up the law of cosines that I have on our formula sheet, and I just have them copy and pasted here. I want to mention for a brief minute that when we're looking at a general triangle that not necessarily doesn't have a 90-degree angle in it, you might start to see something that's a little bit familiar. If I cover this up a little bit, a squared plus b squared equals c squared. That should look familiar. In fact, when you look at something like that, that should remind you of the Pythagorean theorem. But that only happens for right triangles. And so we have these two sides, a and b, we square them and then add them up, and that should equal c squared. So what's happening there is this must be the angle C, capital C, and it must be 90 degrees. And if C is 90 degrees, cosine of 90 degrees is 0, meaning this whole piece is multiplied by 0, meaning this whole piece is gone, and I have a very specific triangle that very specifically gives me the Pythagorean theorem. So Pythagorean theorem, although great and wonderful, and we know it from a young age, it's just one special case of the law of cosines. If this angle C is not 90 degrees, if it's 91 degrees, we need this. If it's 92 degrees, we need this. If it's 89.5 degrees, we need this. If it's 17 degrees, we need this. Right? So every other triangle uses the law of cosines. There is only one triangle, the right triangle, that allows us to omit this little extra piece here. And of course, it all depends what the longest side is. I'm using this third one as an example because this will be the longest side. But these are just labels. All right, this could be C, this could be A, this could be B if I move things around and change this to the angle B. So again, the A's and B's and C's are just labels, and that's why there are three different versions. But really, if you just memorize one of the formulas and the pattern for that formula, you already know the other two. You don't have to memorize. You just have to know this one formula and the pattern it exhibits, or the longest side and the angle, or however you want to look at it when you look at these sides in terms of not just Pythagorean theorem, but with this extra bit tacked on. Just know that the side you're looking for is the cosine of that angle that corresponds to that side. Right, so this is a really great way to handle, like I said, more generic triangles. And you can see that if you solve for cosine, you can also use this to find angles. Right, so cosine of A would be A squared, subtract B squared, subtract C squared, and then divide by negative 2bc. That's just simple algebra. That gets you a whole new formula where now you can find the angle. And if you really need the angle, you need cosine inverse of all that stuff so you can get the angle out of it, which we'll use. So make sure you have your calculator ready for this section. It's going to be quite a bit of plugging stuff into calculators because you'll see we just want A, and this is A squared, so we're going to have to end up taking the square root of all this stuff. If we just want B, this is B squared, we're going to need to take the square root of all that stuff. Right? Same thing for C, we would need to take the square root of all that stuff. So some heavy computation, but the algebra or the arithmetic will all be done on the calculator, and then we'll approximate where necessary using significant figures. But these are the formulas, and I just wanted to show you that nice little application that gives us Pythagorean theorem, and it only happens in that one specific instance. Now, this law of cosines is good for when you're finding yourself in a situation where you're given triangles that are of the form side, 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 or if you have side, an angle in between it, and a side. This is where you want to use the law of cosines. All right, remember before we saw that if we had angle, and an exterior side, or an angle, an interior side, and then the angle, that's where we saw in the last section we would use the law of sines. All right, so now we have some situations that we can cover with the law of cosines. Notice that the law of cosines, you need at least two sides. For the law of sines, you need at least two angles. Right, so if you find yourself in a situation where you're not sure which formulas to use, this will help lead you in the path of which formulas you should go for. And then there's also the case where maybe they tell you all three angles. There is absolutely nothing we can do, because I could have these angles, which are the same as these angles. These, and these, and these are the exact same angle. But who's to tell me if it's big or small, right? Or it could be even larger than this, or it could be even smaller than this. If all I know are the angles, then I don't know the scale of that triangle. So that leaves you hanging in the case where you're just all three angles. There's really absolutely nothing to do. And then here's the fun one. Angle, side, side. No textbook will ever write this because you know why. This is where you can use either law of sines or law of cosines. This is actually a really nice case where it doesn't matter which ones you use. Of course, all textbooks will write side, side, angle to make sure they get published. These are all the different cases we're going to be dealing in this section specifically with law of cosines. So these are the situations we'll see in 7.2. So let's get some practice. And I want to do one of each case to start off with. Let's see, to start off, we'll do a side angle side. Get rid of that line. And let's take a look at find all missing parts of triangle A, B, C. Where, finish this off, they will tell you that lowercase a is 412 meters, lowercase c is 342 meters, and capital B is 151.5 degrees. So again, we want to find all the missing pieces. This is quite a large angle, 151.5. So to get my triangle down, something to reference, I'm going to put a big angle in my triangle and put that 151.5 degrees in the big angle, just so it makes my picture kind of match exactly what I'm going for here. I've got, this is capital B, so this must be lowercase b. Now I have a choice of where to put A or C. I think I'll put angle A here, which puts A over here. There's 412 meters, which means I'm forced to put capital C here, which means little c, 342, must be over here. And again, since we want to find all the missing pieces, I'm just going to make a list so that I can keep track of everything I have and everything I still need. I have capital B, so let's just write that in there. Have lowercase a, so let's write that in there. Have lowercase c, so let's write that in there. We can see that on the bottom. Yeah, okay. So our goal is to find the missing pieces. And look what situation we're in. We've got a side, an angle, and a side. All right, so we have two sides and an interior angle, which tells us that we should be using the law of cosines. Let's start by finding that side B. Notice if I tried to use law of sines right off the bat, I have this angle and I can do sine of B over B, which I don't know, equals sine of C I don't know over C. Oh, well then there's two unknowns, I can't use law of sines. Same thing happens if I try and do it with A. There's two unknowns, I can't use law of sines. All right, so law of sines will leave you just stuck at a dead end anyway. Eventually you realize you have to use law of cosines. Now, the one for law of cosines is going to be b squared equals a squared plus c squared minus 2ac cosine b. Again, if you know the pattern, you don't need to know all three. Once you have that pattern down, you just fill in the blanks. And since I want b and not b squared, while I'm at it, I'm going to take the positive square root. It's always going to be a positive square root because it's the length of a side. Length's not going to be negative. So I want to do a squared. This was our a, 412 squared. Plus I want to do c squared, lowercase c, 342 squared, minus 2 times a, which is 412, times c, which is 342, times cosine of the angle b. That was this angle that we had, the only one that we had, 151.5 degrees. All right, so go to your calculator, put it all in at once. If you have it all in at once, I went ahead and just already computed it just for the sake of saving time. I don't know if this will pick up. Well, it picks up pretty nicely. All right, so you try and plug it all in at once. It's cut off a little bit because it's scrolled over. That way you're not, approximating this and then subtracting that approximation from this and then approximating with the square root again. Like, don't piecemeal it. Put it all in at once and then hit enter once. And you should get b is approximately, we need 3 significant figures, right? Because see how these sides all have 3 sig figs. So we're going to do the same thing. We're going to say b is 731 meters. All right, now my calculator, again, I got something like 731.0032, right? You know how to round that. Get that out of there. Okay, so now we know this side. Technically, we could jump to law of sines, right? Sine of b over b is sine of a over a, and then I would find capital A. But be careful, we haven't talked about something called the ambiguous case, which we'll talk about in 7.3. And again, I always say this, you want to use the information that they gave you as much as possible, right? Rather than relying on some other information. But in this case, we're just kind of stuck. But stick with law of cosines so that you don't have to worry about this ambiguous case that, again, we don't know what that is yet, but it'll be an issue once in a while. So we'll have to cover that in the next section. But let's say we want to find capital A next. Again, there's no order. You could totally go for capital C for now. But let's say we want to find capital A. Well, then we can look at our law of cosines. And the first one that we have there, if we solve it for A, we would get cosine of A is A squared minus B squared minus C squared over negative 2BC. Which means if I want to find A, it's going to be cosine inverse of this entire A squared minus B squared minus C squared over negative 2BC. Which in our case, now we just have to plug in all these sides. Right? So we just have to plug in all of these numbers. So we want cosine inverse of 412 squared minus B is 731 squared minus C is 342 squared all over negative 2 times B is 731, C is 342. Right, so the top, all those numbers need to be squared, but not on the bottom, right? We're just plugging in B and C as they are. And we get A is approximately, and I already went ahead and did it, and we need to round it, 15.6 degrees. Right, so again, this angle has a half angle in it, so we'll round that to the nearest tenth, 15.6 degrees. Right? We'll be as accurate as they are. So now at this point, you've got 2 of the angles, right, 15.6 degrees and 151.5 degrees. Yeah, you can just go for it, right? If you want to find capital C, we know there's 180 degrees in this triangle, So we can just do 180 degrees minus 15.6 degrees minus 151.5 degrees to get our final answer to be 12.9 degrees for C. This must be capital C. So this gives us all of our missing pieces. Oh, let me fill it in there. Of course, all three of these angles should add up to 180 degrees, which it looks like they do. The largest angle opens up to the largest side. The smallest angle opens up to the smallest side. So everything looks like it's in agreement. So we're good to go. Chances are, if you get something weird, it might be an error in your calculator, the way you typed it in your calculator, because this is quite a bit to type in all at once. So do take your time. And again, this is a degree, so make sure that you're in degree mode. And hopefully none of us get a negative angle or a negative side. That means something really went haywire. You probably got a plus or a minus out of whack. This is a nice case for a side angle side, where we can use the law of cosines, because right off the bat, we definitely can't use the law of sines. So the other situation that you might come across is, what if they give you a triangle and they give you all three sides? Can you find all three missing angles? And actually, yes, you can. So that's the other situation. Same setup, find all missing parts of triangle ABC, where we'll say lowercase a is 51 centimeters, lowercase b is 24 centimeters, and lowercase c is 41 centimeters. And so this gives us a triangle where, when we look at it, A is the largest side. So just going to kind of emphasize, maybe like the bottom here will be the largest side. That'll be side A. C is also pretty large, but B is pretty short. And maybe I could have done a better job of emphasizing one of the sides being shorter. And it doesn't have to be perfect, but let's call this short one over here 24. That's B. Let's call this long one on the bottom 51. And this one remains on the side over here. That would be 41. So that gives us a triangle that sort of looks like what it should. And again, you might draw yours differently. You might draw the longest side on the top or on the left or on the right. Orientation doesn't matter. What matters is, can we find capital A, capital B, and capital C given this information? And the answer is, of course, yes, we can. And C is 41. So if 24 is little b, then this must be angle B. 41 was C, so then this must be capital C. Here's 51, so this must be capital A. Just to make sure I get my labels correct. So now what we have to do is just go through and use law of cosines. This is a perfect situation where we have a side, side, side. So that tells us to use law of cosines. Just in no particular order, let's say we want to find capital A. All right, so again, if we solve it for capital A in that very first formula that you see over there, we want cosine of A squared minus B squared minus C squared over negative 2BC. Or sorry, not cosine, cosine inverse, right? So looking at our formulas, subtract b squared, subtract c squared, and we have to divide out by that negative 2bc. That leaves us with cosine of A, but we want the cosine inverse so that we can just have it solved for and ready to go. Now, what this allows us to do is go to the calculator and plug in cosine inverse of, again, here's A, right, 51 squared minus, here's B, 24 squared. This is why we draw the picture. It's easier to find all these things in the picture So we can go through and find all the pieces that we need. So if we plug that in our calculator, and again we have to approximate it, we should get something that is about 100 degrees. Oh, oops, do that blue. Now we don't know the either two angles yet, so we're also going to have to rely on this for finding capital B. We'll need cosine inverse of b squared minus a squared minus c squared over negative 2ac, which in our case gives us cosine inverse of 24 squared minus 51 squared minus 41 squared over negative 2 times 51 times 40. All right, so again, you can start out with the law of cosines formula and solve for cosine B to get that ratio, and then just take the cosine inverse to actually pick up the angle B. Then we just go to our calculator and we do a bunch of plugging and chugging. You get something like 27.6 something. So we're going to take that and we're going to round that to 28 degrees. So now at this point, we just need this last angle. So it's fine. We can just do 180 degrees minus 28 degrees minus 100 degrees to see what we actually get left over, which is 52 degrees missing for capital C. At that point, you're just grabbing that last angle. Probably less likely to make a mistake by plugging it in to just 180 minus the other two angles. So that's your law of cosines for a side case. So main thing is, again, practice knowing those law of cosines, practice, knowing those formulas. Obviously you have the formula sheet, but you can see that you don't need to memorize all three and then memorize a brand new one for the angles. As long as you know the first one and exhibit that pattern with any side you choose, be it A, B, or C, or if you find angle A, B, or C, it doesn't matter. As long as you know that pattern and you're comfortable with the arithmetic, the algebra of moving them around and solving for different variables, then you should be fine. And if at any point in this video you go, hey, what the heck is this guy doing? Why is he going so fast? Again, feel free to email me questions or, pause and actually do these computations. Don't just stare at me do it and go, wow, that looks easy, or wow, that looks hard. Make sure you're doing it on your calculator. When you see me write it down, pause the video, type it in your calculator, then unpause it, see what I get compared to what you get. All right, that's the only way to know if you're doing it right, is if we're getting the same numbers. We want to match. Right? We want our numbers to be the same. So now I want to do a problem that's a little bit different style, a little more geometric. It says the diagonals of a parallelogram are 14 meters and 16 meters and intersect at an angle of 60 degrees. And it wants us to find the length of the longer side. So we'll call this a word problem. This is a nice application for the law of cosines. The diagonals of a parallelogram just looks in general something like this, are 14 meters. So I'll try and draw one in green. 14 is smaller than 16, so the smaller diagonal is the 14. The larger diagonal, the 16 one, is here. And they intersect at an angle of 60 degrees. Well, 60 degrees is acute, so it's got to be this angle. Now, this whole, the whole point of this problem is to find the longer side. I'm just going to label it, I'm going to call, they're both top and bottom are the same, but we'll look at the bottom just so there's more space. I'm just going to call it A. Let's just give it a variable. I'll call it A. That's the longest side. So I want to find the distance from here to here. Now, this whole red diagonal is 16 meters. This whole green diagonal is 14 meters. What I'm going to do is I'm going to focus on this triangle right here. I don't need to use the whole parallelogram. I'm just going to focus on this triangle on the bottom, which means I know that this side over here is half of 14. It should be 7 meters. This long side here should be half of 16. It should be 8 meters. And this angle here, well, if this is a straight line, then these two angles are supplementary angles. So this must be 120 degrees. Right, if this is a straight across diagonal, then that's 180 degrees. 120 and 60 is 180. So if that's 60, that has to be 120. So you can see the information they gave me, and I color-coded it for you. But that's not the information we're using, because we want this longest side. So I'm just going to focus in on this triangle down here. And there it is. Now we can see we're in a situation where we've got side, angle, side. Here's my side, my interior angle, and my other side. So this is definitely a law of cosines. And I want A, so that is A squared equals B squared plus C squared minus 2BC times cosine of A. Or I'm calling this 120 angle A because it opens up to little a. So it's a nice application. Again, I'm just going to go right for the square root since we need to do it anyway. Now we've got B and C. It doesn't really matter. Those are interchangeable, right? Which ones you call B or which ones you call C. So I'm just going to say B is the smaller one, 7 squared, plus C is the larger one, 8 squared. Notice I'm not using the 14 and the 16 and squaring them, because this is the full side 14. That's the full side 16. I'm not using those as sides of my triangle. And of course the 120. It's actually a very nice angle. But we'll just go to our calculator and see what we get. And it gives us A is, this one's actually exact, 13 meters. So we actually get a really nice number out of it. That's our longest side. Just be careful if it asks for the shortest side, you would do the same thing, but notice for the shortest side, you might use that 60 degrees instead. So it'll change that number because it'll change this to cosine of 60 degrees. But you'd still want to take half and take half to make sure you got the correct answer. All right, but just to mention again real quick, you can kind of see why B and C, it doesn't matter because they're not the longest side, they're the shorter sides. It doesn't matter if you interchange them because 7 squared plus 8 squared is the same as 8 squared plus 7 squared. And of course, multiplication is commutative. 2 times 7 times 8 is the same thing as 2 times 8 times 7. So this number will be the same with those swapped. And these two numbers, you're going to add them together. You get the same result anyway. So our longest side for that parallelogram must be 13 meters. Which makes sense because the diagonals going through it need to be longer. And then while we're at it, another word problem, another nice application for us. This one's going to say that two planes Two planes leave an airport at the same time. And it says, well, their speeds are 130 miles per hour and 150 miles per hour. And the angle between their courses is 36 degrees. And it wants to know how far apart they are. How far apart are they after 1 hour? Well, let's get a picture to wrap our heads around this. So they just say that the angle between them is 36 degrees. It really doesn't matter how you draw it. They never even mention north, south, east, west. So I'm just going to take my airport. I'm going to send one plane out at 130 miles in 1 hour. So he's about there. The other plane is 36 degrees. And he goes, let's draw it a little bit longer, 150 miles in 1 hour. So one goes a little further than the other. I'm kind of exaggerating it there. And they want to know how far apart are these two planes. So one's here, and our goal is to figure out how far apart they are. And again, notice they said that the angle between their paths is 36 degrees. There it is. Side, angle, side. Which means now I can use my law, and again, I'll just call this lowercase a. I can use my law of cosines to find little a, if I call this angle A. So little a, let's just jump right on it, is going to be the square root of, again, B and C are going to be interchangeable for us, so I'm just going to say B is the smaller one. B squared is 130 squared. C squared is 150 squared. Minus 2 times B is 130, C is 150. Cosine of the angle between those two planes is 36 degrees. So again, we go to our calculator, and we get A is about 88.59. Look at their significant figures. We can just comfortably say 89 miles apart. Realistically, we should say 90 miles apart because these are not accurate down to the ones place. Right, there are two significant figures here, but unfortunately this number is too small. It's not a 3-digit number. Technically this would be correct, but I'm okay with that. Leave the sig figures for your science class. I just want to make sure you know this formula and you know how to apply it. And give me a solid whole number. Now there's one exactly, well not exactly, but there's one like this in the textbook. It is number 31. It's basically the exact same problem, but this, it asks you for 1.5 hours. So what do you think you would do? I know this is tough asking a webcam a question. Well, what do you think you would do if the problem was virtually exactly the same other than just 1.5 hours? Well, what you'd have to do is extend these by multiplying them by 1.5. This would extend out 1.5 times further. So you'd need 130 times 1.5 to get the plane the rest of the way out. Then you'd have to extend this by multiplying by 1.5. It goes 150 miles in 1 hour, so at 1.5 hours, multiplied by 150 gets it out here. And then you'd be finding a larger distance. So you should get something larger than 90 miles apart, but nothing too crazy, maybe like 100, I'm just ballparking it here, maybe something like 100 miles apart or something, maybe 105 miles apart. So if you want to kind of mirror a problem, that's a great problem to mirror. But pretty much that's it. That's all I got for law of cosines. It's mostly boiling it down to, making a more general version of Pythagorean theorem. Pythagorean theorem, you have to have that 90-degree angle. Law of cosines, who cares, right? Who cares what the angles are? As long as you're falling into the situation where it's side angle side or side side side, law of cosines is the best way to go. Right? Law of cosines is a very, very powerful formula, or formulas, depending on which side you have it solved for, or which angle you have it solved for. So let me know if you have any questions. And then in 7.3, we'll revisit some of this law of sines and law of cosines, and we'll talk about something called the ambiguous case, which is a little tricky, but not too tricky. Best case scenario, you identify there is no ambiguous case. Second best scenario, you identify there is a second case, and you have to kind of break it into two separate triangles. And what I mean by that is, I'm not going to get into it too long here, but you could have this triangle or this really skinny triangle, right? Because you don't know where this side is, because you don't know this angle. If this angle is unknown and you don't know you're dealing with a small side or a long side, then you have to account for both cases. So that'll be 7.3. So I will see you there.